very short talks on specific topics that the project deals with. Today we're having introduction to security and resiliency in electric power, and that will be done by Professor Pete Sauer from the University of Illinois. And anyone who's anybody in power is just a couple of degrees of separation from Pete. We're proud to know him and have him on the program. The second talk today will be from Arthur Conklin from the University of Houston, who is our domain expert in resiliency of oil and gas systems. And if you get into this field, you will find that there are similarities and differences, and in fact we have a report on that. The point of these talks, and so I'm going to, for all the speakers, it's short, 20-ish kind of minutes, introduce the topics, hit the high points, and mainly, identify where to go for further information, which means go talk to Pete and Art. So without any further use of time, I'll turn it over to Pete.
Okay. Oh, do I need a microphone?
You don't need a microphone.
I don't need a microphone. I'll just
by the room.
Okay. Thanks, Al, and welcome everybody to the inaugural onboarding session for CREDC. Mine is called Electricity Primer. I've heard it's called Primer, but I don't know what. It's also called Big Wire Basics. The electric power people are called the big wire people, not to be confused with the computer engineers and computer scientists that are the little wire people, or the wireless people. So I'm going to talk on behalf of a lot of people. This is our CREDC organization. It's big and it's very broad. It covers the whole geography of North America. There's a traditional power system operating state concept, and the top of it says preventive or normal state. That's when the lights are on and everything's fine. It could survive also a list of contingencies. If you simulate loss of a generator, loss of a line, loss of a load, the system is still okay. That's what makes it the normal state. If you could not survive a contingency, one of those accidents, then you go into the alert state. And so there actually is a different state in the control center, and you're on alert. And you have a certain amount of time to fix that. You have to make it safe for all the contingencies on this list. And I'm pretty sure there were at one time governors and mayors involved in that list. I don't know that the president ever got involved, but the governors of the states did. In which contingencies should you study? Because it's going to cost money to make it safe. And so somebody has to say to the utility, you must obey the loss of that generator. And the people, the operators, will change their generation to make it survive the loss. And if it actually happens, the system could go into the emergency state, which is load is not being served, lines are being lost, the middle of a blackout, and then you go to the restorative state and bring everything back to the normal state. So this has been around since the 1960s, mainly after the New York blackout. The contingencies, what are they? Well, it's the loss of a transformer, a line, a major load, and what are the causes of these things? Storms, tree growth, that was the recent 2003. Breakdown in age, you have insulation failure on insulators. Squirrels and snakes, they get into the equipment. Poor or careless maintenance, just plain mistakes. Sabotage, disgruntled employees could cause this, or a terrorist. There are cascading outages, which are triggered by one of those above, and then they create another one. And finally, I put down the hackers. I put them in the same category as the squirrels and the snakes that could cause a contingency. And what does it mean to survive a contingency? Well, you got three things that we worry about. Thermal, you have to keep everything within its rating. Kilowatts, amps, the things that are leading to thermal problems. Voltage, you have to have all the voltages good within a range. And finally, it has to be stable. It has to be in synchronism, and what it really means is all the mathematical equations with all the constraints that you can think of are being satisfied. So we have a mathematical model to go with all of these things. And just in case you're not familiar with some of this technical stuff, voltage is probably the most important concept. It's the separation of charge, and it creates electric fields in between the two pieces of charge. Or you can think of it as two conductors. In our houses, it's 120 volts or 240. Out in the cities, the distribution, 12 kV, and it's usually overhead, and it's bare. The wires don't have any insulation. In the cornfields, it's very high voltage, 345 kV, and it's overhead, and it's bare. And the reason we go to high voltages is that for the same amount of power, you use less current. And you like low currents because the losses are smaller. And I'm speaking of current. What is current? Well, voltage is the separation of charge. Current is the movement of charge. So you have so many coulombs of charge moving down a wire and coming back on another wire. And these currents create magnetic fields rather than electric fields. And yeah. Oh.
Can I ask a question very quickly?
Yes.
So I was always wondering, I mean, I'm so used to 12K and 345, but why? Why these particular values? Optimizing for what?
Are you one of those hackers out there, Sergey?
I might be, or I might be a squirrel.
Okay, well, a lot of the voltage levels have evolved over time. They're typically multiples of 60, 50, for some reason. 345 is probably an evolution from something lower, like 230, and it might be a square root of 3 times 230. I don't know. I never thought about it. But 345 is standard here in the Midwest. 500 kV is pretty standard in the East and the West. The highest voltage in North America is 765 kV. And I don't really know where those numbers came from, Sergey, but they're more or less industry standards that have evolved over the years. And they're probably multiples of some common number.
I see.
But there's nothing sacred about them. There is a 1 million volt line in China, but not here in North America.
Wow.
Okay.
Thank you.
How are these? You're welcome. How are these voltages and currents related? Well, voltage is created by a source. You buy a source, battery, generator. Its only purpose is to create a voltage. And we pay for kilowatt hours, but you don't, I mean, a kilowatt hour is some strange quantity. What people really understand is voltage. As long as you got 120 volts in your plug, you're happy. A blackout is when the voltage goes to 0. So the voltage is what's the most important thing, and it comes from a supply or a source. The amount of current that flows in the grid depends on the resistance of the load. The resistance is a quantity that describes the behavior of the device. There are 3 fundamental laws that we have to obey, and actually these fundamental laws are used in cybersecurity in various ways. If we want to see if somebody's messing with our numbers in a SCADA system or in a state estimator, we check to see whether the data satisfies the Kirchhoff's laws or Ohm's law. And we can check that because we have a model. So Kirchhoff's voltage law says Some of the voltages around a closed path is 0. Kirchhoff's current law says the sum of the currents entering a node or a point is 0. And Ohm's law says that the current is the voltage divided by the resistance or impedance of the load. One other important thing about these laws is they can't be repealed by any congressional body. And there's 2 H's in the word Kirchhoff. Okay, here's an example of Ohm's law. 12 volts on the left there. That could be a battery or an AC supply. 6 ohm load. Could be a light bulb of some kind. You take that voltage, you divide it by the 6 ohms, and you get 2 amps. So Ohm's law is V equals IR. So the 2 amps times the 6 ohms equals 12 volts. And we assume that those wires are perfect, so there's no voltage drop in those wires. Or the other way to think of it is 12 over 6 is 2. Then there's parallel connection. A parallel connection is what is used everywhere in every place. The only thing that wasn't parallel in the past has been Christmas tree lights and some runway lighting in airports. For the most part, everything in your house is parallel connected. So you have a supply, 12 volts on the left. You have a 6 ohm resistor, which we had a minute ago. That gives you 2 amps. Now I add another resistor in parallel, 4 ohms, and 12 over 4 is 3. So that's the current for the 4 ohm load. And Kirchhoff's current law says that the 2 plus 3 equals 5, the total current in that parallel combination. So this circuit satisfies Ohm's law and Kirchhoff's laws. And they determine how the current flows in the lines and how the voltage is distributed around the grid. In this case, there's only one voltage. In a series connection, you could think of it as modeling the resistance of the wire, 1 ohm, and the load is 11 ohms. The wire is a perfect short circuit, so it should have a small resistance, right? So you take the total resistance there is 12 ohms, and you got 12 volts across it. That's 1 amp. So that 1 amp flows all around in the circuit in the series connection. And by Ohm's law, 1 volt is lost across that 1 ohm resistor, and 11 volts across the load. So it satisfies Kirchhoff's law. Some of the voltages around the closed loop is 0, and it satisfies Kirchhoff's current law because there's only one current. Were there any other questions out there? Okay, types of electricity. There's DC and AC. And DC comes from batteries, fuel cells, and electronic converters. It's constant, so it's literally a straight line over time. The alternating current you get from rotating machines, because when you rotate a magnet, you naturally get this oscillation, and that's what the primary voltage is for our grid. And you can think of that as Nikola Tesla's contribution, and the DC part is, who was the other guy? Thomas Edison. He had DC power, Nikola Tesla had AC power. 3-phase, we use 3-phase, not single-phase. Single-phase has a pulsating power. If you multiply the voltage times the current in time, you get a double frequency pulsation, which will ruin a shaft. It'll break it. So we don't use single phase that much. We use 3-phase because with 3-phase you get the pulsations canceling out so that the total is a constant. Nice, smooth torque. Power and energy, what's the difference? Power is work that you do. It's work. You divide that by time. And so it's energy per unit time, and power is the rate at which energy is used. So if you lift a 100-pound kid 6 feet in the air, and you do it in 2 seconds, it takes 300 foot-pounds per second. That's 100 times 6 divided by 2. That's the same as about 400 joules per second, which is the same as 400 watts. And that's the same as 0.4 kilowatts, which is about half of a horsepower, 746 watts in a horsepower. And we typically pay for kilowatt hours, 10 cents a kilowatt hour. So it would cost you, if that 0.4 kilowatts is used for a whole hour, that would be 0.4 kilowatt hours, and that would cost only 4 cents. Okay, reactive power. This is one of my favorite subjects. Was just talking about it over lunch. We call them VARs, volt amperes reactive, VAR. And I plot here reactive power on the vertical axis and real power on the horizontal axis. And we do that because there's a thing called complex power, where P is on the real axis and Q is on the imaginary axis. The P is what you pay for, 10 cents a kilowatt hour. The VARs are actually free. You don't have to pay, as long as you don't use too many of them. An AC motor, on the other hand, uses an inductive coil to create the rotation. And a coil absorbs VARs. It's a form of power, but it's a zero average power. So half the cycle it's consuming it, and the other half it gives it back. So over a sine wave of power, the reactive power gives it to you for half the time, and then it takes it back. So on average, it's zero. That's why it's free. It doesn't cost anything, because on average, it's not consuming anything. Okay, some basic power system components. This is a famous picture off of somebody's website. On the left is the generation, the fuel, the furnace, the boiler. Then there's that thing, a transformer. That's called a step-up transformer, because the generator probably generates at about 23 kV or so, 20 kV. But you want to get it up real high so that the current gets smaller. So for transmission, in the middle there, we have the 345 kV and so on, where we go long distances. And then we have a step-down transformer at the other end, which brings the voltage back down for us to use. And it might typically go down to 12,000 volts for your neighborhood, and then it supplies the loads at even lower voltages at the distribution level. So that's the basic power system component slide, and I was going to show all kinds of slides of the pictures, but you get tired of seeing all those transmission lines and loads. The question is, who's in charge of all this stuff? Yeah.
So, sorry to interrupt again, but going back to the previous slide, I was completely mind blown when I learned for the first time that people sell reactive power. Could you comment on that? And this is not in this picture, right? But,
yeah,
you know.
Sergey, I'd be happy to talk about that. A normal motor consumes reactive power, so it has to have it. Now, if you just turn on an air conditioner, that motor is going to consume some reactive power, and you're going to be using it. Somebody has to provide that for you. And the default is the utility company. It comes over the wires into your house from the generator. As long as you don't use too much of it, they won't make you pay for it. But if you use too much, you're making the current out on the grid too high, and they'll charge you for that. Now, you can get your own VARs yourself by just buying some capacitor banks at your local capacitor store. And these are big capacitors. we don't talk about farads and stuff like that. We talk about kilovars and megavars of capacitance.
It's quite a size.
Well, the capacitor provides the vars for the inductor. That's the difference. If you remember your circuits, the inductor is a positive reactance, and the capacitor is a negative reactance. So the capacitor gives you the power when you need it, and then the inductor gives it back to the capacitor, and so they just trade back and forth. And then nobody provides the vars except the capacitor, and that doesn't cost you anything except the cost of the capacitor. There's no hourly charge for the vars that you're using. So I don't know who sells these vars. I suppose I did have one person call me up and say, I read your article about vars, and you said in there that everybody has to have vars, but they don't cost anything. I want to get into that business. And it sounds good. Everybody has to have them, and they don't cost anything. So you should sell them. Well, you're competing then with the local utility. Because if you want to try to sell vars to somebody, fine. I'm not sure what that means. If that means you're going to sell them a capacitor, okay, so you have to buy a capacitor. Selling vars is not something you can do over a USB port or internet. It's not a commodity that you can get on a wire except through your power line. And that comes from the utility. So if you're going to try to sell somebody vars, you're going to have to compete with the utility, which doesn't charge anything. Does that cover it, Sergey?
Yeah, it's fascinating. I mean, I understand it as a matter of balance that the utility has to maintain anyway, because otherwise they wouldn't be able to operate smoothly. But it's like I said, it's fascinating.
It is fascinating. I just love it.
Mm-hmm.
I'll keep talking if you want.
Yeah. Well, I shouldn't really interrupt all that often.
Oh, I appreciate it. Thank you for doing that.
All right.
Okay. Who's in charge of all this stuff? Well, there's the FERC. That's the Federal Energy Regulatory Commission. That's the federal U.S. body. There's North American Electric Reliability Corporation, NERC. They were originally just the United States, but they've broadened to include Mexico and Canada. They are an industry group that finally has some teeth, as they say, which means they are the monitors of the reliability for the grid. And if you are unreliable, you have to pay. There are state legislatures. They pass laws having to do with the economics of the rates. We have state commerce commissions, which deal with the companies that have to file for rate increases. We have ISOs and RTOs, independent system operators, and regional transmission operators. These are industry organizations that got together and formed like an aggregator idea. And then we have, down at the lowest level, the poor, lonely balancing authority operators. These are the control center operators that try to keep the frequency at 60 hertz, try to manage at the most economical operations. Those are the people in charge. Here's NERC, North America, and that's an interesting little figure because it shows the 4 grids in North America. The Western interconnection is on the left. Texas is down at the bottom. The Eastern interconnect is that big mass on the right, including Florida. And then up on the upper right is Quebec. So Quebec is like Texas. They're not part of the grid. They are connected to us only through asynchronous ties. Okay, there's a control center. And look at all the computers. Sergey is looking at that and just licking his lips at how much fun it would be to get in there and mess around in that control center.
I wasn't one, you know. I wasn't allowed to mess with, you know, the boards.
Okay, we can move on.
Okay. Here's the list of the software. SCADA, state estimation, power flow, contingencies. AGC controls the grid generation. Economic dispatch, a lot of money involved. And those are all targets for hacking. Protection systems, this is quick. The protection of the grid is to protect equipment primarily. People too, but mostly the equipment. A fault or a short circuit, if you take a two-pronged fork, like you use at Thanksgiving, and stick that fork in the outlet, the two holes, you're going to create a short. And probably won't hurt you, but you shouldn't try it. But the current just goes around the two pieces of the fork and creates a high current, and your fuse should blow or a circuit breaker will trip. So that's a short circuit or a fault. You must detect a fault very quickly, and you must remove it. You've got to get rid of that, otherwise it's going to cause a loss of equipment. Okay, so we use fuses. Everybody remembers fuses that's over 40. They have typically two ratings. A fuse has the amount of current that it's designed to accept without doing anything, like 20 amps. Then it also has a higher rating, like 10,000 amps. That means as long as the short circuit current is below 10,000, it will operate correctly. If you put 20,000 amps into a fuse that only protects you up to 10,000, it will probably just melt and not do anything. It won't open up the circuit. They have time characteristics. It's called the minimum melting time on the vertical axis versus current on the horizontal. So the higher the current, the faster the fuse blows. Relays and circuit breakers, how are they related in this protection business? Relays are the local devices, and they act on what they get from a sensor like a current transformer or a voltage transformer. And the relay is the brains behind the protection. If there's something wrong, the relay will send a signal to the circuit breaker to open up the circuit and protect you against the abnormal behavior. So the relay is just a computer that's programmed to detect certain things, and it has communication because it has to talk to neighbors and talk to circuit breakers. They have time current characteristics also. Here's one of my favorite slides. This is called fuse coordination or breaker coordination. There's a source on the left. The boxes are circuit breakers. Black lines are transmission lines or distribution lines. There's my house there at the bottom. There's Al's house in the middle. And Tim's house. Tim Yardley's not here, but that's okay. Now, if a fault happens in the middle of that one line there on the right, you're going to get a lot of current coming from the source. So, what should you do? Well, you want that breaker that says you want this to open first. You want that circuit breaker to detect the high current first, and then open it up so that the current stops. And Al's house is still connected, and so is mine. The other two relays on the left there are only for backup. If the relay and the breaker on the right fail, then those other ones are backups. And the problem with those are, if you open those up, you've lost everybody. Al, me, and Tim. Okay. We're getting near the end. I'm my last slide, I think. This is just evolution of relays from electromechanical.
Can I ask a quick question?
Yes.
I'm not sure you're going to cover this or not, but could you explain kind of why, for example, I guess there was a monkey tripped a relay in Kenya and the entire country went dark. How does that happen?
Nothing surprises me when it comes to the grid. So I don't doubt that there is a monkey and there is a breaker or a relay that could cause a huge blackout. Most of these relays have manual trips, so if you hit the right button or you inject the right value, it will send a signal to open up circuit breakers. So
I guess the issue, and we've seen this in the U.S. as well, is where it cascades. And the way it was explained to me was if everybody is operating close to their maximum capacity and you lose one source, then all the others are now over capacity, and one by one they all trip out. Am I making sense?
Yeah, that does make sense. It would be a violation probably of our security criteria, which means you have to be able to survive contingencies. So it shouldn't happen, but I can see that in some countries it could. And you're right, that's a very good point. The cascading failure is we call it the 2003 blackout in Ohio, New York, and Quebec. Loss of one line, all that current has to go somewhere else. That causes another line to overheat. And then that line fails, and that current has to go somewhere else, and so on. So that's a good point. Okay, let me finish up here. Or did you have another question? No.
Somebody got background noise.
Okay, electromechanical relays up to digital relays, and they're all run by computers.
All right.
That's it.
Yay.
Okay, all right, thank you. I'm sure people respond by email. Very quickly, as we're introducing Art, Pete did touch on something that you may not have noticed as it went by, which is that we're interested in cybersecurity and resiliency, and where possible, we like to involve the physics. So, for example, I'm very aware of the project that Pete spoke of, where we're observing the network traffic, the commands to and from the relays, the communication between the relays, and we're reconciling it with measurements and saying, does Kirchhoff's law hold? And if not, one of those relays is lying. So this is where you can take the cyber and the underlying physical model and make it work. Anyway, so we're running a little long, Art, so I'll encourage